everybody, Dr. A here. In this video, we are going to be exploring an example of using LRFD load combinations to compute the required shear strength for a given beam. So let's look at our given information. We have an interior beam that is part of some type of frame system, and we are told that identical beams are spaced at 10 feet on center, and then we're being asked to compute the required shear strength using LRFD. So let's take a look at this beam and see what we have here. We have a simply supported beam here. See, we have a pin and a roller, and we have a total span length of 15 feet. We see that 7 plus 4 plus 4 is 15. The beam is supporting a uniform distributed load that is really coming from three things. Notice that we have a Q dead of 30 PSF, a Q live of 100 PSF, and a Q snow, that S is for snow, of 40 PSF. So that's referring to the distributed load here. In addition to that, we have two dead loads that are point loads that are just single forces. We have P dead 1 of 5 kips and P dead 2 of 4 kips, and each of these are located 4 feet away from the two supports. So let's go ahead and get started. I'm going to go ahead and label these supports here. I'm going to label the pin A and the roller point B here. Anytime you're not given labels, you just go ahead and label things yourself. So let's go ahead and write solution. So the first thing we need to notice is that these distributed loads are in terms of PSF, pounds per square foot. And the reason why they are expressed in PSF is because we have a surface essentially that is being supported by several of these identical beams one after another. And so that surface loading is in terms of PSF. And so what we first need to do is determine what the equivalent linear load is in PLF, pounds per linear foot, on this particular beam. And to do that, we multiply the surface loads Q by a tributary width. Okay, now the tributary width is going to come from this 10-foot spacing because we know we have identical beams spaced at 10 feet. So let's go ahead and say W dead is Q dead times 10 feet. And then similarly, W live is Q live times 10 feet. And then, of course, W snow is Q snow times 10 feet. And so when we multiply these out, of course, we get 300 PLF. We get 1,000 PLF. And then we get 400 PLF. Now, just to use consistent units, notice that my point loads are in kips. I'm just going to convert these to KLF. So we'll have 0.3 KLF as our W dead. We'll have 1 KLF as our W live. And then we'll have 0.4 KLF as our W snow. So so now our loading is pretty much ready to go. If you want, you can redraw this beam in terms of the linear loading instead of the surface loading. But for the most part, we're ready to go. So the problem says, what is the required shear strength using LRFD load combinations? So the next thing we're going to do is we're going to reference our LRFD load combinations. Now I'm going to reference ASC 716. So from ASCE 716, and this is going to be chapter 2 of ASC 716, we have load combinations for strength design. That's our LRFD load combinations. Now, I'm going to look at the basic load combinations. We have 1 through 5. Now, notice that our applied loading is including dead load, live load, and snow load, which means that we don't necessarily need all 5 of these load combinations. We just need to look at the applicable load combinations. So to speed things up just a little bit, I'm going to go ahead and tell you load combination 1, we need to investigate that. That's going to be 1.4 times a dead load effect. And then load combination 2 is going to be 1.2 dead plus 1.6 times a live load effect plus 0.5 times. Now, if you're looking at ASC 716, it says roof live load or snow load. Snow load or rain load. Okay. Now, for our problem, we don't have a roof live load and we don't have a rain load. We just have the snow load here. Okay. So we can automatically see that load combo 2 is going to be a little more specific for us. 1.2 dead plus 1.6 live plus 0.5 times a snow load effect. Now, you can go through and look at the other load combinations. We could look at load combination 3. Why don't we go ahead and take a look at load combination 3? That is a potential candidate for something that could govern. That's going to be 1.2 dead plus 1.6 times snow load effect plus 1.0 times the live load effect. And, you know, we could look at load combination 4 from ASC 716. Load combination 4 will not govern over load combination 2. So if you are looking at load combo 4, you'll see it'll never govern over 2 for this particular problem. And then load combo 5 also will not govern over 1 or 2. So these are our 3 potential load combinations, and these are the 3 we need to eventually investigate to see if which one would govern over the others, okay, for the required shear strength for this beam. So what we do is we're going to determine the shear force due to each load type. Okay, so that's dead, live, and snow separately. Okay, so what we can do is look at the dead loads acting on the beam alone and determine what the maximum shear force is due to dead loads acting alone. Then we can determine what the shear force is due to live load alone, and then what the shear force is maximum shear force due to snow load alone is. Okay, so we're going to analyze these by type one at a time, and then we'll apply load combinations after we have figured out the maximum shear due to dead load alone, live load alone, and snow load alone. Okay, so let's do this one at a time. So let's look at dead load alone. Okay, so I'm going to go ahead and draw a free body diagram of our beam due to the dead loads alone. All right, so we have our pin here. We have our roller here, and we call these A and B. And we have this uniformly distributed dead load, and if you remember when we applied that tributary width earlier, we said that that's 0.3 KLF. So W dead is 0.3 KLF. And then at the 4-foot marks, we had a 5 kip dead load and a 4 kip dead load. And here's 4 feet, 4 feet, and 7 feet. Okay, so this is our beam subject to the dead load alone. And then I'm just going to go ahead and use this beam also as my free body diagram. So I'll have an AY here. Of course, we have an AX that's equal to 0 at that pin. And then we have a BY over here. So I'm using my dead load beam diagram as superimposing my free body diagram on top of that with the external reactions. So let's go ahead and calculate these external support reactions, and then from that we can figure out what the maximum shear force is. So how about we just apply some equilibrium equations? You have some options here on how you want to start. I'm going to say some of the moments about A equals 0, counterclockwise is positive. So we'll have negative 5 kips times 4 feet, and then of course minus 4 kips times 11 feet, and then we'll also have minus 0.3 KLF times 15 feet, and then times another 15 feet divided by 2. And then we'll have plus by times 15 feet all equals 0. This is just basic statics. We'll do some calculations here, and we'll end up getting 6.52 kips as our reaction at B pointing up. And then we can apply some of the forces in the y direction equaling 0. So from force equilibrium, we'll have positive AY minus 5 kips minus 4 kips minus 0.3 KLF times 15 feet. And then, of course, plus by, which we just calculated as 6.52 kips equals 0. Doing some arithmetic, we'll get AY equals 6.98 kips pointing upwards. Okay, now those of you who are pretty savvy with statics and structural analysis, you may be able to just look at this and tell that this AY of 6.89 feet, this happens to be V dead max. This does happen to be the maximum shear force due to the dead load alone. Now, if you have trouble seeing that, that's okay. What you can always do is draw the shear force diagram, and by doing that, we will come to the conclusion that that is our maximum shear force due to dead load alone. So let's go ahead and do that for kind of a review and practice. So here is our set of axes. And so moving left to right, AY pushes us up to 6.98 kips. And then we have this distributed load of 0.3 KLF times 4 feet. And so if we take 6.98 minus 0.3 times 4 feet, that pushes us down to 5.78 kips, and that's a linear relationship. And then we encounter that 5 kip point load, which pushes us down to 0.78. And then we have another distributed load segment over a 7-foot length, which will then push us down to a negative 1.32. We hit that additional point load, which then pushes us down to a negative 5.32. And then we encounter another distributed load segment, which will push us down to a negative 6.52. And then we encounter by, which closes us off at 0. And so if we connect our segments together appropriately, we will have a shear force diagram that looks something like this. And then, of course, this is a 4-foot mark. This is an 11-foot mark. And then this is the 15-foot mark. And here's our shear force diagram. Now, I'm not going to go into all the details of this because that's, you should be familiar with shear diagrams from previous knowledge, but this is just a quick review of drawing and sketching a shear force diagram. And then we can clearly see that AY equaling the 6.98 kips is our maximum shear force due to the dead load alone. Okay, now we're going to follow a similar procedure, and we're going to look at live load alone. Okay, so with the live load alone, we can resketch the beam. And when we resketch the beam, we put the live load alone on this beam. And the live load alone is going to be that 1 KLF over the entire 15 feet. And again, I can superimpose my reactions here. And, of course, we'll still have an AY due to live load alone now, and AX is 0, and then we have a BY here. Now, this is a simple case to look at. We can clearly see by symmetry AY equals BY equals 7.5 kips pointing up. And again, by symmetry, we can say that that's 15 feet times 1 KLF divided by 2, and so we get 7.5 kips alone. And again, you could sketch the shear and moment diagrams, or just the shear diagram to help you visualize it, but you will come to the conclusion that this 7.5 kips is V live max. And then in a similar way, we're going to have snow load alone. The geometry of the snow load is going to be very similar to the geometry of the live load, except instead of 1 KLF, you're going to have the 0.4 KLFs acting over the 15-foot span. So for the snow load alone, I'm just going to get right to it. AY, let's color coordinate. How about that? We'll say AY equals BY equals, and we'll have, again, 0.4 times 15 divided by 2, and that will give us 3 kips, which happens to be RV snow max. And again, if you're not confident in this, just sketch out the free body diagram and solve for these external reactions like I showed with the dead load alone, and you'll get to these conclusions. So now we're ready to investigate our applicable load combinations, all right? So we're going to say investigate load combos, okay? And so load combo number 1, all right? We're going to say VU equals 1.4 V dead max, and that gives us 1.4, and this is where we go back to our dead load analysis from earlier, and we get our V dead max is 6.98 kips. So we substitute that in here, 6.98 kips. And let's see what that comes out to be. If you punch this through, 6.98, I'm punching this through in my calculator with you, I get 9.77 kips, okay? Let's look at our next load combo, which was load combo 2. We'll say VU is 1.2 V dead max, and then plus 1.6 V live max, plus 0.5 V snow max, and we can substitute these values in from our previous 3 analyses. So 1.2 times 6.98 kips plus 1.6. My V live max was 7.5 kips plus 0.5 times 3 kips, and then punching this through in our calculator, let's see what we get. 1.2 times 6.98 plus 1.6 times 7.5 plus 0.5 times 3, and we get 21.88 kips. Now let's investigate that last possible load combination, load combo 3. And from load combo 3, we had a VU equals 1.2 V dead max plus 1.6 V snow max plus V live max, okay? Or 1.0 V live max. So this load combo 3, let's see what we end up getting. 1.2 times 6.98, and then we add to that a 1.6 times 3, and then we add to that just a 1.0 times 7.5, so we get 20.68 kips. And so we can clearly see that load combination 2 gives us the worst case scenario for the shear force, the shear force that this beam could be experiencing according to LRFD load combinations. So we're going to say load combo 2 governs with VU equals 21.88 kips. So in a design situation, what you would do if you were designing or checking this member for shear force using LRFD, the LRFD load philosophy, you would use the 21.88 kips as your ultimate shear in a shear design or shear checking scenario. So that concludes this video. If you found this helpful, please hit like and subscribe. Thanks.